Hello, this is Mr. Collier, and today we're looking at vector properties, starting from the basics, so the very definition of what a vector is first. Okay, so some notations. Vector A, we write it as, or you can type it with a bold A, or by hand, we write it with an arrow above it to indicate a vector. And a vector indicates direction here, not in particular a position. So the direction of this, sort of like a slope, is like 3 right and 1 up. Okay, so the way to write that in vector form in a column vector is 3, 1. The top number indicates the direction in the horizontal direction, or the direction with the x-axis. And the bottom one is y-axis, so that might be a little bit backwards for some people. For B, this is -1 and up 2, I guess, right? So again, that's the x direction and the y direction. Okay. You can also write an ij. So these are unit vectors. So I is 1 unit to the right, and j is defined as 1 unit up. So you can also write b as -1i plus 2j, and a you can write as 3i plus 1j. Okay, so you see both of these on IB exams. Now the magnitude, it's, well, basically this distance here. You can get it by Pythagorean theorem. You can see I've got the triangle redrawn, right? Okay, so the magnitude, and we indicate that with these vertical bars, sort of like absolute value, right? Absolute value of a number is the distance away from the origin, and the magnitude of a vector is also a distance from, I guess, the beginning of the vector, which is not necessarily at the origin, I suppose. So the magnitude is here of A is root 3 squared plus 1 squared. It's like Pythagorean theorem. So it's root 10. Okay. So the magnitude of B is root 1 squared, or -1 squared, plus 2 squared, which equals root 5. Okay, let's check out this next question. A vector has a magnitude of 10 and is in the direction of 30 degrees above the x-axis. So let's represent that. Magnitude of 10 means this length is 10 and we're at 30 degrees here. So that's a special triangle. It's a 30, 60, 90 triangle. So this value is half. This value is 5 root 3, right? So write this using ij notation. Okay, so we can represent that. Let's just call it C equals the x direction. It's, oh, actually we don't want to call it a vector. We want the ij notation. So it's 5 root 3i plus 5j. Alright, so addition and subtraction of vectors. Let's represent them on this grid first. A plus B. So let's take a look at A. A is 1, 2. I'm going to start over here somewhere. Okay, so it doesn't matter where you start because this just indicates direction. So remember, this is xy. So this is 1 in the x direction and 2 in the y direction. We're up here. This is the vector A. Now B is basically 4 right and 1 down. Okay. So, for example, if this was motion or something, if you go this way and you go this way, you've really gone total of this. Okay. This represents A plus B. All right. Now, if you look at it, A plus B. If you look at on the graph, This is 1, 2, 3, 4, 5 to the right and 1 up. So that is 5, 1. And also notice that you just add the components together. If you add this, you get 5, 1, like in the graph, right? Okay, so graphically, yeah, you can see it graphically, and you just add the coordinates together. This makes sense. If you go right 1 and then later you go right 4, it's like you've gone right 5. So that's how you add vectors. Subtract vectors, well, to represent that graphically, let's draw it again over here. Oops. Let's say, actually, a little more to the right. Let's say that's A. And we're subtracting B. That's like adding negative B. So I can go backwards now. Here. Okay. So this is negative B. And the resulting vector is here. This is A plus negative B or A minus B. Okay, now if you just subtract them, you get A minus B equals negative 3, 3, which matches what we have here. We have negative 3 in the x direction and 3 in the y direction, right? 2a plus 2b, well, we can do that down here. 2a minus b is like you do 2 times 1, 2 minus the b is 4, negative 1. Okay, that is 2, 4 minus 4, negative 1. So you get negative 2, 5. Graphically, now this is A, right? So this is double A, is 2A. Okay, and this is minus B again, and I wish I would have drawn a little bit to the right here. Hang on. This is A, 2A. And that's negative B, so again, we're going this way. The resultant vector is right there. And is that negative 2, 5? Yes, it is. This is negative 2, 5, right? So the graph's going to match just adding and subtracting the components of each vector. Okay, so sometimes we write vectors like this, where we have a starting point and an ending point, okay? We call the ending point the head and the beginning point the tail sometimes. So we're going to find AC and CA. Let's check it out. AB is 1, 4. Let's do that here. Let's call that A. And then we go 1, 4. That's B. So this is the vector AB. Okay, go from A to B. The order matters. BC is negative 1, 2. And I barely left myself any room. Negative 1, 2 is right there. So that's C right there. Now you can see from looking at this thing, we can see what AC is. AC, and the direction matters, it's going that way. This one drawing the arrow, the direction matters. You can see that AC is 0 in the x direction, and 1, 2, 3, 4, 5, 6 in the y direction. Okay, and how do you get that from these numbers? You just do, it's equal to you can do AB minus BC and get that actually, right? Or the other way around. 0, Well, actually, you can just add them together. Of course, you can see graphically, you just add them together, you get AC. So that's just 1, 4 plus negative 1, 2 gives you 0, 6, right? Okay, so if you have AC, summary, AC is just equal to AB plus BC. Okay, it's like if you go from A to B and then B to C is the same as going from A to C, so it makes sense, right? CA is this way. That's CA. From C to A is just the opposite direction. So CA equals, what have I got written there? CA is the opposite way around, so that's, oh, I've got that backwards anyway. It's 0, -6, which means down 6, right? Okay. Yeah, so let's take a look at some here. So AB, if you're going from A to B, it's 1, 4, okay, and BC is this, and AD is that, find DC. Okay, so we can think about it this way. DC is like you're starting at D and going to C. Okay, so this, we have AD here, but that's starting at A, but you can do DA. If you go from D to A, and then you go from A to B, and then you go from B to C, then you get DC, right? That logically makes sense. DA is the opposite direction of AD, so it's like -2, -3, plus 1, 4, plus -1. Oh, well, that's a fraction. Common mistake. -1, 2, right? And then just add the components together, and you get -2, 3. So DC, you can draw it out, you'll get to the same conclusion, -2, 3. Okay, parallel vectors. Well, let's plot some of those. 1, 2 is like there. 2, 4 is like you go 2 to the right and up 4. Okay, 2 right, up 4. Okay, but it's in the exact same, direction, right? So they're parallel. And if we have that one, we go in this direction, -1, -2. So they're all parallel. Okay, and we call them all scalar multiples of each other, right? So like 1, 2 times 2 equals 2, 4. So they're scalar multiples of each other, right? And then 1, 2 times -2 equals -1, -2. So whenever you have a scalar multiple, they are parallel. We call it scalar multiple because we're just multiplying by a constant number instead of a constant. Called a scalar in vectors because it kind of scales a vector, right? If you multiply this vector by 2, you double it. So that's why it's called a scalar multiple. So anytime you have parallel vectors, they're scalar multiples of each other. A unit vector is, by unit, it means 1. It's got a length of 1. Okay, so it's called a unit vector. So let's take a look at this vector. This vector is like -5 and 12, right? -5, 12. That's the vector right there. Okay, but that is longer than 1. How long is it? Well, we can write like this. This is the notation. 2 vertical bars for the magnitude, and you just do Pythagorean theorem. The negatives always cancel, so you can kind of ignore them. That's actually 13. Okay, so if you want a vector in the same direction, but of length 1, then you got to do 1/13 times that vector to get a vector with a magnitude of 1. Okay, so the unit vector here is just going to be -5/13, 12/13. That's the unit vector. And you can always just multiply by 1 over the magnitude of the original vector. So to get unit vectors here, find the vector in the same direction with the magnitude. It's not a unit vector, it's getting you a magnitude of 15. Okay, so let's get the magnitude of this one. Okay, the magnitude of that is, by Pythagorean theorem, it's obviously 5. So this is kind of obvious. To get 15, we do 3 times this vector will give us a magnitude of 15, right? So the answer, I guess, is -9, -12 is the vector in the, -9 is positive. That's the direct vector in the same direction with a magnitude of 5. Okay. Now if we want 7, I guess we could do, we can bring this down to, we can multiply this vector by 1/5 to get a unit vector, and then to get 7 we just multiply by 7, right? Or just multiply by 7/5. So that gives us 21/5 and negative 28/5. Gives you a magnitude of 7. Okay, position vectors. So this, you can write coordinates of points as a position vector. So the point -1, 2 is here. The vector to get to that point is like that, and obviously it is just going to be written as -1, 2. Okay. So we write it as OA because we go from the origin, which is O, to A, and it's written like that, or a little lowercase a. Okay, so we've got a couple vectors here. If C equals 1, 4, and D equals this, give the position vectors of C, D, and hence find the vector CD. Okay, so to do that, let's represent that. So we got 1, 4. CD is 1, 4. And so let me just represent that. We go 1 and then a 4. Okay. Sorry, that's not correct. Those are coordinates. Oops, those aren't vectors. So C, let's kind of represent like this. 1, 4 is C. 1, 4. D is at 2, 3. Okay. So to get from C to D, we gotta go, so CD must be go right 1, down 1. Okay, right 1, down 1 is the vector CD, logically, just by looking at the geometry of it, right? But notice you can just get these numbers by doing just by subtraction, right? So the vector, the position vector OD is 2, 3. We'll just do 2, 3 minus, if we change this to a position vector, 1, 4 gives us 1, -1. Okay, so what we did there, we just subtracted, we did OD minus OC. Alright, so whenever you have a vector, like for example CD, you can take the second one and minus the first one, because the second one's where you stop and C is the beginning. Okay, so this is equal to OD minus OC. Okay, we can call it sometimes head minus tail. Head minus tail. In 3 direction, you have 3-dimensional vectors too, in 3-dimensional space, and we have x-axis. Let me try to make a 3D graph. Sometimes we draw it like that, or actually, let's do it more like that. X, Y, Z. That's a horrible graph. Imagine this coming up from the page. Okay, the Z direction. So we use the unit vector k for that. So this is x, y, z coordinate. Anything within 2 dimensions can be extended in 3 dimensions. So we could do all the same kind of stuff. Like for example, AB equals OB minus OA. Second one minus the first one. Head minus tail. So OB is 2, 3, 2 minus, and then 1, 2, 4. Which is 1, -5, -2. So that's the vector.